Hey everyone, so we're going to continue with part 2 of the simple linear regression activity here. So we already looked at checking of model assumptions for this Scrabble dataset problem. Now we're going to look at influential points and outliers, which are also potential problems when using a simple linear regression model. So influential points and outliers are two different but related concepts. Influential points are observations that have a significantly large effect on the regression estimates relative to the rest of the data. So observations can be an outlier and influential, but they can be also one or the other. So not every outlier is influential, and conversely, not every influential point is an outlier. So how we can identify influential points formally is we'll use Cook's distance measure, commonly referred to just as Cook's D. So each observation has a Cook's D value. And if it's big enough, we'll say it's influential. So specifically, we're going to use a cutoff of 0.5 in this class. Although note that there's not a consensus in the field of statistics, and this is a rule of thumb I think I got from Penn State University's Department of Statistics. Okay. So let's see, for this Scrabble data set, are there any influential points based on our criteria? So we're going to look at Cook's D value. So we look at this plot, Cook's distance plot. Okay, how R gives this plot, which is how most software does, it gives you the Cook's distance value on the y-axis, and then the observation number is the x-axis, so that you can find which observation or which value is potentially problematic. And then R also labels, the way we did the R code, which is included at the bottom of this document, R also labels problematic points with the observation number. So here the fifth observation has a really high Cook's distance measure, Cook's D measure. And then observation 17 and 26 have decently high values, but they're not above 0.5. So we could, this data set's small enough, we could literally look up the observation row for 5, 17, and 26. Okay, so 5 is the most problematic. So we can see, if we scroll up to look at the data, in the 5th row is letter E. Okay. Letter E has a Scrabble point value of 1, and it has a relative frequency in English writing of 13%. So what that means is it occurs very frequently relative to other letters, it looks like. 13% is the highest. But its point value is small, okay, which is what we would expect. But it's an influential point, likely due to this value being so high for the x variable, the predictor variable. So anyway, we look at the Cook's distance plot, and the only one that's above 0.5 is the 5th observation here. So there's one influential point, one straight up and down line that towers above 0.5. So there it is. So there is one observation that is influential, which has a Cook's D value above 0.50. And specifically, it looks like it's about 0.09-ish. So that's how we look for influential points. How you would handle that, so what that means for real life data when you're conducting predictive modeling, is that this single observation has a significant influence on all of the predicted values. So what's happening is that if we look at the scatter plot, we can probably see where it's at. Okay. It had a Scrabble tile point value of like 1, and the percent in English writing was 13. Okay, so it looks like it's here. This is the letter E, because it has 13 for the percent relative frequency. Okay. What happens is that because this point is so far out, it's so influential, it's able to pull the regression line up towards itself. It has much more what we'd call leverage. If you think of this like a seesaw, the regression line works like a seesaw, where points in the middle, in the very middle of the cloud of points, have less leverage to pull or tip the regression line one way or the other, as compared to points that are really far out on the edges on either side. Points that are really far out on the edges, so outliers in terms of the x variable, have much more leverage, much more influence, we say, over the regression line and can pull it up towards itself. So like if this point weren't here, if we excluded it and refit the regression model, probably it would look something more like this. So maybe it wouldn't be tipped as up as much because this point's pulling it up and it resulted in it being a little bit higher. Okay, and that affects the predicted values for all the points. So it's potentially making the predictions worse for every other point at the expense of improving its own predicted value a little bit. So it's a greedy little point. It's influential is the formal term for it, but it's problematic. For like Scrabble data, it's not a big deal to remove that point. We could remove that data point and refit the model if we wanted to get good predictions. But again, it depends on the context. If you're looking at like a public health measure, like you're relating lead levels in pipes to lead levels in, say, children's blood, it maybe isn't ethical to just remove a point to get a better trend in your points that you want. You can't just hand pick out data points. But again, if you're doing, Scrabble points, it's not a big deal, Scrabble letters. Or, if you're doing marketing analytics, maybe it's really important to get a good predicted value for marketing strategies. So maybe it is good to remove a data point if it's super influential. Okay. So it depends on the context, but we get to make that decision. And sometimes you can just always fit the model both ways. Fit it with the point included and fit it without the point included. Compare the predicted values you get from each model. That's a good approach too. Okay. All right. So outliers are a different type of problematic point. Outliers are not necessarily influential, but there are points that have very large residuals in magnitude. So in other words, their predicted value is very different than their observed response value. To formally identify outliers, we are going to use what's called studentized residuals, which are like standardized residuals. So if you're familiar with z-scores, which are standardized values or standardized measures, studentized residuals are sort of like standardized or z-scores of residuals in a way. You can think about it like that. And they're standardized sizes that account for varying units of measurement problems might have, or different scales on which a problem might be set in. Okay. So we're going to consider a point for any data set to be an outlier if it has a studentized residual that's bigger than 2 in magnitude. And so here, let's look at the Scrabble data, see if we have any outliers. And so here, R calls them standardized residuals. That's what we're looking for here. Okay. And we have the leverage as well, but we're not interested in the leverage. In this activity, we're not going to be looking at it. We're just saying, do any points fall outside of -2 and +2? Okay. And here there are 2 points. They're really close on top of each other, so it almost looks like one. But it's observation 17 and observation 26 are above this 2 threshold. Okay. So if we drew a straight line over here, 5 is corresponding to this point, so it's below this 2 mark. If we drew a line down at -2, it'd probably be like down here. And there's no points below that. So anything below this -2 mark or above +2 are outliers. So we have 2 outliers here. Observations 17 and 26. So observations 17 and 26 have standardized. So I'm kind of using standardized and studentized residuals interchangeably, that term. That's what we can do here. Okay. Okay, so we're saying those are both outliers. Outliers don't necessarily affect our predicted values very much, especially if they have smaller leverage values. Okay, so 17 and 26, if we looked at their Cook's D values, yeah, these had Cook's distance measures that were a little big, but not that huge. Okay, so more what this does is this will affect the normality assumption. These are likely what contributed to the normality assumption being violated. And yep, we can see 17 and 26 outliers. So outliers more have to do with violating the normality assumption. So if these weren't here, the normality assumption would be looking a lot better, but there's still some problems in this data set. Yeah, one could argue maybe they're contributing to the homoscedasticity issue we looked at earlier too. What would you do? So influential points, I would say, is more of a consideration of fitting the model with and without that, with and without the influential points included, and seeing how your results differ. Outliers, I don't know if that makes as much sense to do that. I think it more means that if you have outliers present, probably your model assumptions are violated, which means that the p-values and prediction intervals you would get with your model are no longer valid. That's what that would mean if you have outliers present, which is the same as what it means if your regression assumptions are not met. That means your p-values are no longer valid. Prediction intervals that you can obtain from the model are not reliable. And potentially your predicted values are not great, but it doesn't definitively mean that. But it does mean our p-values are questionable and our confidence intervals and prediction intervals are bad, no longer reliable. Okay. So we had some problematic points. Our assumptions were violated. We had some influential points. We had one influential point. We had some outliers. A lot of problems going on in this data set. But it's better to be aware than, blissful ignorance, I suppose. Okay. So even though assumptions are not met, we're proceeding for the sake of the problem. So let's interpret the estimated slope by starting with the blueprint interpretation of the slope here. Okay. There's our blueprint of the slope. Let's copy that. All right. Okay, so for every 1% increase in the relative frequency of a letter occurrence, in English writing. It's a mouthful. Let's see. I'm going off the page there. Let's see if we can. Yeah, there we go. Okay. So for every 1% increase in the relative frequency of a letter's occurrence in English writing, we expect its Scrabble tile point value to, and then if we look at the slope estimate, beta hat 1, just going to get this beta hat 1 symbol so we can say what it is. Beta hat 1. Okay, beta hat 1 is we look at the regression output right here, minus 0.59. So for every 1% increase in the relative frequency of a letter's occurrence in English writing, we expect its Scrabble tile point value to, and then because this is negative, we expect it to decrease by 0.59. So we don't have negative numbers. We want to exclude negative numbers from interpretations for the most part. And we just say decrease by this amount instead. Okay. So we never want to have a negative number in a slope interpretation. Okay. Now let's interpret the estimated intercept. So for the intercept, let's see, we have beta hat 0 is equal to this number, which we got from here in the output, 5.64. So here we would say the expected Scrabble tile point value So if a letter never shows up in any English writing, it would be really hard to play. So we're saying we'd expect Scrabble developers, creators to mark it as about 5.6 points. Okay. So note that Scrabble tiles only come in whole numbers, right, for the point values. So it may be tempting to say like, oh, we should make this 6. You could, but it's okay to get, it's sensible to get decimal numbers as predicted values from a linear model. That's okay. It's sensible. So we can keep it this way. We actually want to keep it this way. We don't round it like that. Right. So that's the expected Scrabble tile value of a letter that never shows up in English. Let's suppose we had a new letter lambda that has a percent relative frequency of 2, what would we expect its scrabbled point value to be? Okay, so this is where we will use our estimated regression equation to answer this question. So we're going to get a predicted value. Okay. So 5.64 minus 0.59 times 2. And we can use Google to answer that. It's its primary purpose calculator. Okay, 4.46. Okay. So we can obtain a predicted value like this by using the estimated regression equation ourselves. But note that we can use R to calculate predictive values for us. So like in this table down here is that predict. Okay, so let's pick back up there. Okay. So the video cut out a little bit there, but we were talking about the interpreting the slope, interpreting the intercept, and then getting a predicted value. So we got this predicted value for a new letter that has a percent relative frequency of 2. And we calculated that using the regression estimates ourselves, putting in a little bit of legwork by hand. R can directly calculate those values for us by fitting a regression model in R. And so here's R calculating that number exactly. And it's slightly different due to just rounding of the regression estimates when we used them, but otherwise it would be exactly the same. So here was the table, for example, for obtaining a predicted value for a letter that has a percent relative frequency of 2. And then here's its interval. Okay. So let's see. So given this predicted value for a letter that has a percent relative frequency of 2, actually G, if we look at the table of data, the letter G actually has a percent relative frequency of 2. So we got a predicted value for that was about 5 or 4.5 points for the point value, but it's actually 2. The actual Y response value is 2. So what that means is that our Y hat for G, oops. Let's see. Okay, so we calculated a Y hat for G of 4.46, since G has a percent relative frequency of 2. Its actual Y value is 2. Okay, because if we looked up here in G, it's right here. This 2, not this one. This 2, okay, is the actual Y value. And in general, we can calculate a residual value, which we denote with E, as being the actual minus the predicted value. Okay. Which in this case, that means our residual is equal to we use Google again, minus 2.46. So we can have residuals that are negative. G has a negative residual. because the predicted value was bigger than the actual observed response value. Okay. So this is the residual value. All right. What about if we had a new letter that had a relative frequency, percent relative frequency of 20? What would the predicted value be for that? Well, it would be like this. Okay. Negative 6.16. That's the expected point value of that new letter. That's problematic. Not just because it's a negative number, like that is a problem in itself. We would not report that, since we know Scrabble tile point values are bounded above 0, we would not report this as being the number. But like we have to use our own sensibility to not say negative numbers when it does not make sense in the context. So it's important to note that is one issue with this predicted value. So what the main issue here, besides it being negative, it's not reliable due to this being what we call extrapolation. Because 20 is outside the range of our observed predictor variable, we cannot obtain a reliable predicted value at this value. Okay. So because 20 is outside the scope of our data set, outside the range of our observed data set, we can't get a predicted value at it. If we look at the scatter plot, okay, graphically, it's like we're getting a predicted value way out here at 20. We can only get valid predicted values in between the biggest and smallest x values in our data set. We're constrained to that area for making valid predictions. Okay? We cannot assume that this trend will continue on forever outside the scope of our data. It may. It's possible. Not likely in this case, because we see it's negative numbers, but you might have other data sets or other contexts where it could be that the trend does continue, but we cannot know for sure unless we had more data. And you would need to collect more data out in that range of X in order to make predictions out that far. Okay. I mean, sometimes you have no choice, but if you do make predictions out there, it's called extrapolation, and it's considered, not proper statistical practice. It's not necessarily going to be reliable predictions out there. Okay. So no, because that is extrapolation. And let's see. So, okay. So we got this predicted value from R now. So we got it from by hand before, but if you use the R code at the bottom of the document, you can get a table here that has the predicted value at a percent relative frequency of 2. And then here is a lower bound. This is for lower. And an upper bound for in this case, this is for a 95% prediction interval. Okay, and it's given above or below. It's supposed to be below. So, oops. So you'll probably see the table below. So we can interpret this by saying that we expect. Okay, so I'll give a blueprint interpretation, and then I'll do it for this problem for the prediction interval. We expect y to be between lower bound and upper bound values. You know, for a 95% confidence interval, it'll be 95% of the time. Okay, and then we say actually it needs to be given that x is equal to, and then in this case it's whatever we were getting the prediction at, so it's 2. Okay, so we'll say it's like x star very generally. Given that x is equal to x star, we expect y to be between this number and this number 95% of the time. All right, so how can we do that? So this is like a blueprint interpretation. Let's see how we can do that for this problem. For the Scrabble data. Okay, so for the Scrabble data, let's start with the blueprint. We can say that given that a letter has a percent relative frequency of 2, we expect its Scrabble tile point value to be between lower, which is 0.18, and the upper bound, okay, from here, is 8.73. 95% of the time. Or in other words, we would expect 95% of letters with a percent relative frequency of 2 to have a Scrabble tile point value between 0.18 and 8.73. It's maybe not super meaningful in this context, considering that all Scrabble tile values are between 1 and 10. So this isn't very useful. But you know, you maybe have other contexts where a prediction interval would be more insightful, like again with the marketing analytics example, maybe you need a like range of reasonable outcomes for what happens with X amount of advertising spending. Okay, because you get one predicted value, but that doesn't describe the amount of uncertainty you have in the possible outcomes for sales. Okay, so a prediction interval in tandem with the actual predicted value gives us our best estimate or prediction for what's going to happen. But then also the interval expresses our uncertainty in our predicted value. And so that's very useful in itself, being able to express the uncertainty. As we have a bigger data set, if we had more observations, this prediction interval would get more and more narrow. The range would be smaller and smaller, and it would center in on the predicted value itself as we for the most part, as we got more data. I mean, it doesn't eventually narrow in completely on the predicted value, but the idea is this could be a little bit more narrow if we had a larger data set. There always might be some underlying level of uncertainty, no matter how big your data set is potentially. But anyway, the prediction interval is helpful for quantifying uncertainty in our predicted values is the main takeaway. So the last thing we'll look at is that if we remember back to these assumptions not being met for this model, so what do you do? we checked all the assumptions. Where was it? Here. And many of them were violated, right? So whenever you have a upward bend in the QQ plot like this can suggest that you have a right skewness to the residuals. Sometimes when that's the case, it can be helpful to use a log transformation of the response variable y and use that as your response variable instead. This is a common trick that people do or use in linear regression. Okay. So here, for example, in R, we calculated the log of the Scrabble tile value and instead are modeling that using the percent relative frequency in English writing. So log is a function that we can use, and it's a nice function. So just every positive number you can calculate the log of. So for example, log of 1 is, the natural log of 1 is 0. The log of 1.1 is 0.04, and log of 2 is 0.3. Okay. And log has this nice property that if a number, so log you can only calculate for positive numbers. If one number is bigger than another number, so if x1 is bigger than x2, then log of x1 is always bigger than log of x2. Yeah. And this is what we call a monotone function. Okay. It preserves ordering of the relationship here, and so that's why it makes it an okay transformation to use of the response variable for regression. You could also use the square root transformation. Sometimes people do that, but the log I think is more popular because it has some nice statistical properties to it. So anyway, it's what people do sometimes. So here you can see when we did the log transformation, the relationship looks a little bit more linear than before. It's a little better. It's not perfect. Okay, and then we just have the new model estimates for the log transformed response. Okay, so notice our R squared is a little higher. That's good because in general, a higher R squared, a higher adjusted R squared, both are better. Okay. So how can we compare which model is doing better here? Well, if you ever want to compare two simple linear regression models, we can use the AIC and BIC values here. Okay. These stand for Akiki's information criterion. I'm probably butchering that name, so I am so sorry to that professor, that person who came up with this information criterion. And then we have the Bayesian information criterion. In general, a lower AIC and BIC value is desirable for a model. So a model is preferred if it has a lower AIC or BIC value. I'll write that down. In general, so it's more desirable or has better quote unquote fit to the data than a model with higher AIC or BIC values. These both typically tell the same story. Sometimes they may disagree. In my personal opinion, I rely on BIC if I'm using these information criterion measures. But generally, often they'll just tell the same story about which model's better. Okay. So here, look at these BIC and AIC values for the log transformed model, 42 and 46. If we looked back at our original model, the AIC and BICs were much higher, okay, over 100. So since the log transformed model has lower AIC and BIC values, this fits the data better. Okay. And so we can also, the reason that matters, what we're saying is maybe this will give better predictions, better predicted values for our data set using the log transformed model. Okay, so how can we get a predicted value from the log transformed model? Well, we start off a similar way to what we did before. Okay, so we're going to use our new estimated regression equation to get a predicted value. All right. Now we have a different, for the log transformed model, our estimates are different. And this is now on the log scale. Okay, so it's kind of like y hat star, which is the log Scrabble tile point value, what we estimate for that. Okay, so if we have this is our regression equation, then plugging in 2, we get, because x is not log transformed, we just can plug in 2 like that for x, and then we get 1.24. Okay. And so if we want 1.24 is the predicted log Scrabble okay. So this is where the cost comes in for doing the log transformation. Okay, we're no longer on just talking about Scrabble tile point values. We're talking about the log of the Scrabble point value, which is not what we were interested in at the start. You know, and again, thinking about another example, if you're talking about sales, advertising expenses and relating that to sales, if you do a log transformation of the sales, you then get a prediction for the log sales, which is not the same. Okay. If you have like $10,000 that you predicted for sales, then the log of that is actually 4. Log of 10,000 is 4, the natural log. So this is not on the scale that we want, but fortunately, you can undo the logarithm of a value using the exponential function, it's called. We can exponentiate it. So our predicted Scrabble tile point value is given by, and we do e to this power and if we calculate that with Google, like this, we find that it's about 3.45. So we'll just round it to 3.46. In E is a number just like pi. It's E for Euler's number. So what is Euler's number? The Euler's number is like pi. And here it is. It's like 2.7182. It's like pi. It goes on forever. It's what we call an irrational number. So that E you can use to undo the natural log function, which is what we used here. Okay, so it allows us to get our predicted value. Okay. And you can use the, like how I got it, E to 1.24, you can do E and then the little caret symbol, which is if you do Shift 6 on your keyboard, that's how you can get E to the 1.24. So that's our predicted Scrabble tile point value. Okay, so if we compare that to our original model that was not log transformed, remember we got about 4.46. Okay, so kind of similar, but it's different. And so this is where maybe like we would rely more on the Scrabble tile point value for the for our predicted value. This one, we would rely on the log transformed model, maybe because it has BIC values that were lower and AIC values that were lower. Okay. So we won't, I won't show you a log transformation problem on an exam or a homework, but we're just going over it in this activity. Okay, so you'll see slightly more simple examples, but we're just going over this because it's the activity together. Okay. And as usual, the R code for implementing everything we did here, fitting the model, getting output, is appended at the end of the document. Okay. So that's it for simple linear regression.